Welcome to our Quantum Deep Dive.
Hello.
Today we're taking a close look, a real deep dive into the fascinating world of hybrid quantum classical autoencoders.
Indeed. And our guide for this exploration is an insightful essay by Jörg O. Schneeppert titled Hybrid Quantenklassische Autoencoder, KI neu definiert.
Right. Our mission today is to unpack the key concepts from this essay. The architecture, training, applications, challenges, and the future possibilities of these systems.
We're sticking purely to the insights provided in Schneeppert's work here.
So the big question for you listening in is probably, why did this combination matter? Why should you care about mixing quantum computing and AI like this?
Well, because, as the essay strongly suggests, these hybrid systems, they really promise to redefine how we handle massive data sets.
Redefine? How so?
They could potentially let us tackle problems that are, frankly, just beyond what our current classical computers can manage. It's about building a bridge to, new computational territory.
Okay, let's unpack that. Let's start with the core idea, this synergy, classical meeting quantum.
Yeah. At its heart, a hybrid system is exactly what it sounds like. It blends the proven strengths of classical computing with the, let's say, emerging power of quantum computing.
Classical computing, that's deterministic, sequential, right? Like the device you're listening on now. Very reliable for structured tasks.
Exactly. It follows instructions step by step. But quantum computing introduces, completely new ways to process information.
Using things like superposition.
Right, superposition, where a quantum bit, can be a mix of 0 and 1 at the same time, and entanglement.
Ah, yes, where qubits get linked in that spooky way, affecting each other instantly no matter the distance.
Precisely. And these properties, they allow quantum systems to explore many possibilities at once and handle complex correlations in a way classical systems just physically can't.
So the hybrid approach uses the classical systems we have now, which are great for many things,
and combines them with the unique power of quantum computation, even with the quantum hardware we have today, which is still, developing.
You're not waiting for the perfect error-free quantum computer. You're using the quantum piece where it adds something special.
Exactly. The essay highlights fields like optimization, simulating complex systems, think physics or chemistry, and especially machine learning.
Where these hybrid methods might give us speed-ups? Better results?
Potentially, yes. Significant speed-ups or higher precision for certain kinds of problems. That's the promise.
Okay, to really get the hybrid idea, maybe we should quickly touch on the classical building block first. What exactly is a classical autoencoder?
Sure. So classical autoencoders, they're a really core concept in deep learning, mainly used for data reduction and reconstruction.
Data reduction? Like summarizing data, but in a smart way.
That's a good way to put it. The goal is learning a compact, sort of compressed representation of the input data.
How does it work? The structure.
Typically, you have an encoder that takes the input data, say an image, and compresses it down into a smaller latent representation, often called Z.
Okay, the compressed bit.
Then there's the bottleneck, that's the compressed core itself. And finally, a decoder, which tries to reconstruct the original data, let's call it X hat, just from that compressed Z.
And it learns by comparing the original X with the reconstructed X hat.
Exactly. It tries to minimize the difference, the error between them, usually using something like mean squared error. And the tighter that bottleneck, the more it has to learn the really essential patterns.
It can't just memorize the input, it has to understand it in a way.
Precisely. It learns the underlying structure. This happens by adjusting internal parameters, usually with methods like gradient descent, to minimize that reconstruction error. We also use techniques, regularization, to stop it just overfitting.
What are they typically used for, these classical ones?
Well, the essay mentions two key things. First, dimensionality reduction.
Making complex, high-dimensional data easier to handle, like visualizing data with hundreds of features.
Yeah, mapping it down to maybe 2 or 3 dimensions you can plot, or just storing it more efficiently. The second big one is anomaly detection.
How does that work?
Well, if you train an autoencoder only on normal data, it gets really good at reconstructing normal things.
Yeah.
But if you feed it something unusual, an anomaly...
It struggles to reconstruct it, the error goes up.
Exactly. A high reconstruction error signals something's off, something unexpected.
Like spotting dodgy bank transactions, or maybe an unusual blip in medical data.
Precisely. The essay gives examples like fraud detection in finance or analyzing medical data for rare conditions.
Okay, that makes sense. That's the classical foundation. Now, the quantum side, what are the absolute basics we need to know?
So the fundamental unit is the qubit. Unlike a classical bit, which is just 0 or 1, a qubit can be in a superposition, a combination of both 0 and 1 simultaneously.
And that's key for that parallel exploration power.
It is. It lets
Yeah.
the quantum system check out multiple possibilities at the same time. Then there's entanglement.
The spooky connection.
Yeah, where qubits become linked, their fates intertwine, regardless of distance. Measuring one instantly tells you something about the other. It's very non-classical.
Still blows my mind a bit.
Mine too. And we manipulate these qubits using quantum gates. Think of them like logic gates, but for quantum states. The Hadamard gate, for example, puts a qubit into superposition. CNOT gates can create entanglement.
And the goal of all this is quantum advantage.
Right. Performing certain tasks much, much faster or more efficiently than any classical computer possibly could.
Like those famous algorithms, Shor's for factoring, Grover's for search.
Exactly those. They demonstrate the potential for, well, exponential speedups on specific important problems.
Okay, so we have classical autoencoders for data compression, anomaly detection, and quantum computing with superposition, entanglement, this potential for speedups. How do you actually build a hybrid autoencoder? Where does Schnepp's essay say the magic happens?
Right, this is the core of it. The main idea is to weave quantum algorithms into the autoencoder structure, especially to boost how it handles really high-dimensional or complex data.
So instead of the whole thing being classical.
A key part could be quantum. For instance, the essay suggests the step where the data is compressed into that latent space, that Z, could be done by a quantum circuit. So Z equals quantum of X.
Interesting. So the classical part might prep the data, clean it up.
Exactly. Pre-processing. Then hand it off to the quantum module for the really heavy lifting, the compression or feature extraction.
And then the classical part takes over again.
Yeah, for post-processing the results from the quantum part and maybe doing the final reconstruction step, it's about distributing the tasks.
So quantum for the complex, parallel stuff it's good at.
Right, exploring those high-dimensional correlations. And classical for the bits that are, well, easier or more efficient classically. The essay even mentions you could have multiple layers, mixing quantum and classical components.
What do these quantum components actually look like?
Often they involve something called parametric quantum circuits, or PQCs.
Parametric, meaning they have knobs you can tune, adjustable parameters.
Exactly like that. They're sequences of quantum gates. But the operations of some gates depend on parameters you can adjust during training. Think of it like a quantum neural network layer.
And a specific type is the variational quantum circuit, VQC.
Yes, VQCs are a very common approach. They're a type of PQC.
Why are they important?
Because, and this is crucial, their parameters can often be optimized using classical techniques.
So you run the VQC on the quantum computer, get a result.
Measure the outcome, right. Then a classical computer compares that outcome to what you wanted, calculates an error using a standard loss function,
and then tells the quantum circuit how to adjust its parameters, like classical backpropagation, but for a quantum circuit.
That's a good analogy. It's this hybrid loop. Quantum computation guided by classical optimization. It's central to training these systems.
And this VQC could be in the encoder part, doing the compression.
Yeah.
Or maybe the decoder.
Both are possible. The essay notes they can be integrated into either the encoder or the decoder, depending on the specific architecture and task.
And the classical side isn't just handling data in and out, it's actually running the training optimization loop.
Absolutely. Classical optimization algorithms like gradient descent are key for tuning those quantum parameters. The whole training is a hybrid optimization challenge, finding the best settings for both the classical and the quantum parts together to minimize that overall reconstruction error.
Okay, training this hybrid beast sounds tricky. What are the big roadblocks the essay points out?
Yeah, there are definitely significant challenges, mostly tied to the current state of quantum hardware. Noise and decoherence are huge ones.
Meaning the quantum states get messed up easily.
Exactly. Quantum systems are incredibly sensitive. Environmental noise can disrupt qubit states, and decoherence is basically the loss of that quantumness over time. Both lead to errors in the computation.
Making the results potentially unreliable.
Right. Then there's the fact that current quantum computers have a limited qubit count, and the qubits they do have suffer from relatively high error rates.
Which limits how big or complex a problem you can actually tackle.
Precisely. It restricts the size of the quantum circuits you can run reliably, which directly impacts the scale of the hybrid autoencoder.
Is progress being made on these fronts? What are the solutions?
Oh, definitely. There's a huge amount of research. On the hardware side, people are working hard on fault-tolerant quantum computing. The essay mentions things like the surface code.
Using extra qubits to protect the important information.
Essentially, yes. Building in error correction at the quantum level. And on the training side, as we mentioned, those hybrid optimization algorithms are key. The variational quantum eigensolver, VQE, is a prime example of that classical loop guiding the quantum part.
So using classical smarts to manage the imperfect quantum part.
That's the idea. The essay also hints that specific quantum optimization algorithms themselves, like QAOA, or techniques like adiabatic quantum computing or quantum annealing, might be useful within the hybrid framework for certain tough optimization subproblems.
So the field is finding clever ways to work around current limits while pushing the hardware forward.
That's the essence of this whole near-term hybrid quantum computing approach, yeah.
Okay, we've got the building blocks, the architecture, the training challenges. Where could these hybrid autoencoders actually make a difference? What applications does SNEPAT discuss?
Well, a big one is data compression, especially for, big data.
Because the quantum part might find better ways to compress.
Potentially, yes. Its ability to explore high-dimensional spaces might lead to more effective compressions, squeezing data down with less information loss. The essay mentions handling floods of data from, say, IoT sensors.
Or maybe compressing high-res images or audio files.
Yes. Image and speech processing are mentioned too. The idea is compressing large media files while keeping the quality high and maybe even doing it faster. Another major area is anomaly detection.
Right, we talked about the classical version. How does quantum help here?
The thinking is the hybrid approach could be better at sniffing out really subtle or complex anomalies. Maybe the quantum component can capture faint correlations in the data that a purely classical method would miss.
Useful in cybersecurity, maybe. Spotting weird network traffic.
Exactly. Cybersecurity, financial fraud detection. But also potentially in science, like spotting unusual signals in health monitoring data or astronomical observations.
Using that quantum knack for finding hidden connections. What else?
A very natural fit seems to be quantum chemistry and material science.
Because those fields deal with quantum stuff already.
Precisely. Hybrid autoencoders could be used to compress and analyze the huge data sets generated by simulations of molecules or materials, finding patterns in how molecules bind or predicting properties of new materials.
Speeding up discovery in drug design or materials engineering?
That's the hope. Helping analyze simulation data, like calculating binding energies or understanding semiconductor behavior more efficiently.
Okay, so lots of potential across science and industry. But looking ahead, what are the really big hurdles still remaining, according to the essay, and what's the ultimate vision?
The essay is pretty clear that major technological barriers are still there. We fundamentally need better quantum hardware. More qubits, much lower error rates, better coherence times.
To handle truly massive real-world problems.
Right. And it's not just the quantum chip itself. There's the challenge of seamlessly integrating the quantum and classical parts.
Making them talk to each other efficiently.
Yes. Minimizing communication latency, developing software that can effectively manage these two very different computing paradigms working together. That's a big engineering challenge. Hardware, software, communication. It's all intertwined.
So, lots of practical engineering needed. What about the theory?
That too. There's ongoing theoretical and practical development needed. We need better quantum algorithms specifically designed for these autoencoding tasks, and we need to keep refining those hybrid optimization techniques so they work better with the noisy quantum devices we have now, and the ones coming soon.
And it takes a village, right? Not just physicists or computer scientists.
Absolutely. The essay really stresses the need for interdisciplinary work. Physics, computer science, mathematics, engineering, they all have to come together.
Okay, stepping back for the really long view, where could this all lead eventually?
Well, the long-term potential is pretty profound. These hybrid systems could influence fields beyond the obvious ones, maybe biology for analyzing incredibly complex genetic data sets or helping predict how proteins fold.
Or even social sciences, understanding complex networks.
Potentially, yes. Analyzing large-scale social network data or modeling complex behaviors. And looking even further out, the essay suggests these hybrid autoencoders could be building blocks for more, autonomous systems.
Self-learning, self-optimizing systems.
Maybe. Systems that can learn from complex data streams in real time, adapt, maybe integrate with other advanced AI techniques. Think revolutionary applications in robotics, personalized medicine, areas we're just starting to imagine.
Wow. Okay, so to wrap up our deep dive, drawing heavily from Jurgo Snepat's essay, These hybrid quantum classical autoencoders are a really potent mix,
Yeah, blending classical reliability with quantum potential.
offering new ways to tackle data, especially big, complex data. We see promising applications in compression, finding anomalies, scientific discovery.
But, and it's a big but, facing very real hurdles with today's quantum hardware and the whole integration piece.
Still, they represent a concrete step, bridging that gap between classical and quantum computing.
And their potential impact is huge. They could fundamentally change how we process information in science, in industry, becoming maybe an indispensable tool for complex analysis.
Which brings us to a final thought, inspired by Yurgo Schneppet's work. As we keep pushing the limits of both classical computing and this still nascent quantum computing, could these hybrid systems be the key that unlocks truly intelligent, maybe even self-optimizing systems? Systems that can learn and adapt to challenges we haven't even thought of yet.
It's definitely an exciting and slightly mind-bending future to contemplate.
Thank you for joining us on this deep dive. Goodbye.